After finishing the in-class exercise 1, we can move to model comparison and the delta R-square. Let's review this information. What does R-square mean in Model 1? R-square in Model 1 is 0.145, and R-square equals to the ratio of SSY hat over SSY. The bottom part is total variance in Y, and the top part is variance in Y that is explained by X1. So 0.145 means using expand, we can explain 14.5% of the variance in SAT scores. Next, what does R-square in Model 2 mean? R-square in Model 2 is 0.886. Again, it is a ratio of SS regression with the predicted Y and SS total. The bottom is total variance in Y, and the top is the variance in SAT that is explained by both X1 and X2. So 0.886 means that using both expand and log percent SAT, we can explain 88.6% of the variation in SAT scores. Now we have Model 1, Model 2. We have R-square for Model 1, R-square for Model 2. If we subtract R-square Model 2 from R-square Model 1, we use 0.866 minus 0.145, that is 0.721. That is, after adding log percent SAT, this X2 explained 72.1% of more variance in SAT score above and beyond expand. And this is called delta R-square, the difference between R-square Model 1 and R-square Model 2. So delta R-square is 0.866 minus 0.145, it is 0.721. After adding X2, how much more variance in Y has been explained? So delta R-square is the additional variance in Y explained by X2. In our example, it would be additional variance in Y, which is 72.1%. That is explained by percent SAT, above and beyond expand. After we have the delta R-square, we can conduct a F-test to see if this delta R-square or R-square change is a significant change. If this F-test for delta R-square or the R-square change is significant, then we can also conclude X2 is a significant predictor. It adds more predicted value in predicting SAT scores. Now let's rerun multiple linear regression using SPSS. Let's request the delta R-square. Open the data file, click on Analysis, then Regression, then Linear. Move Expand into Independence, click on Next. Move log percent SAT into Independence. Move SAT into Dependence. Click on Statistics. Check Descriptives and R-squared change. This will give us delta R-square. Then continue, then OK. Here is the SPSS output. We have two models, Model 1 and Model 2. In Model 1, the expand was significantly negatively predicting SAT score. Then we look at the model summary. For Model 1, R squared is 0.145. From ANOVA, we can find out the F-test for R squared. For Model 1, F is 8.18 and it was significant. In this analysis, we also requested R squared change. If you look at the model summary, there is a column labeled as R squared change. For Model 1, it is also 0.145. This is because here R squared change is changed from 0, no predictor, to Model 1 with 1 predictor. So this R squared change is changed from 0 to 0.145. Therefore, it is the same as R squared. Then the F-test for this R squared change is 8.128. The DF between is 1 and DF within is 48. Where DF regression is 1, DF residual is 48. So the significant R squared change, the p-value is again 0.006. It is the same as the F-test in the ANOVA table because it tells us now my model changed from 0 predictor to 1 predictor. And the amount of variance in Y explained by this 1 predictor is 14.5%. More importantly, let's look at the Model 2. In Model 2, we have 2 predictors, expand and log percent SAT. The t-test tells us that expand positively significantly predicted SAT, while log percent SAT negatively significantly predicted SAT score. If we look at the model summary, for Model 2, we have R squared, which is 0.886. This R squared from the ANOVA table, the F-test tells us that it is significant. It tells us using both expand and log percent SAT, we can explain 88.6% of variance in SAT score. More importantly, in this second row, we have R squared change. R squared change is 0.741. It is 0.886 minus 0.145. It is the additional R squared after we adding x2 log percent SAT. Then the F change, R squared change is delta R squared. It is R squared Model 1 minus R squared Model 2. So it is 0.866 minus 0.145, which is 0.741. The F change score is the F-test telling us if this R squared change or delta R squared is significant. So F change score is 305.948. Using DF1 of 1 and DF2 of 47, the F change score was significant. There is a formula to calculate the F change score. It equals to, the bottom part is MS residual for Model 2. So if you look at the ANOVA table, MS residual for Model 2 is 664.646. So the bottom part is 664.646. The top part is complicated. It is SS regression for Model 2 minus SS regression for Model 1 divided by DF regression for Model 2 minus DF regression for Model 1. So if you look at the ANOVA table, it is 243,069 SS regression for Model 2 minus 39722.059. That is SS regression for model 1. Then divided by DF regression for model 2, which is 2, and DF regression for model 1, which is 1. So if you calculate the formula, it is 305.95. That is the F change score. Then you compare this F change score with the F critical score. This model 1 and model 2. Model 1 with just one predictor is also called a reduced model because it only has one predictor, and the model 2 with two predictors is called a full model. Here we have a concept of nested models. We see model 1, where the reduced model is nested within model 2, which is a full model. Okay, so reduced model is nested within the full model. Now we can try to find the F critical score for this delta R square F test. DF between is 1, is 2 minus 1 is 1, and the DF within is 47. So the F critical score is positive and negative 4.08. It was much less than F observed score, so the delta R square is significant. We can extend this knowledge to model comparison for all other nested models. Model comparison test will test the significance of delta R square. The nested or hierarchical models means that the variables in one model represent a subset of the variables in another model. In our previous example, Model 1 has one predictor, which is expand, and Model 2 has two predictors, that is expand and percent SAT. So we see Model 1 is nested within Model 2. When we have two nested models, we can compare if the full model is significantly better than the reduced model. That is, we can test their R square values. Here is another example. Suppose now our model 1 has two predictors, expand and log percent SAT, and our model 2 has four predictors. Besides expand, log percent SAT, we also have pupil-teacher ratio and salary. We can test if model 2 is significantly better than model 1 in predicting SAT score. If model 2 is significantly better, we keep all four predictors. If model 2 is not significantly better, we can just stay with model 1, which is more sufficient, a more sufficient model. So let's run the multiple linear regression for each model. Model 1 with four predictors and model 2 with two predictors. Click on analysis, regression, and linear. Then move expand and log percent SAT into block 1 of 2. Click on next. Then move pupil teacher ratio and salary into block 2 of 2. Move SAT into dependence. Click on statistics. Check descriptives and R squared change. Click on continue, click on OK. Here we have two nested models. The output or the dependent variable is SAT scores. Model 1 has two predictors, expand and log percent SAT. And model 2 will add two more predictors, pupil-teacher ratio and salary. we see that model 1 is nested within model 2. Model 1 is called the reduced model, and model 2 is called the full model. Here is a model summary. Again, model 1 is a reduced model, and model 2 is a full model. Similarly, this is ANOVA for the reduced model and the full model. For the reduced model, with two predictors, R squared is 0.886, and the F-test for this R squared is significant. Therefore, using both log percent SAT and expand, we significantly predict SAT. The R squared change tells us the R squared change from 0 to the R squared based on the two predictor model. So R squared change again is 0.886. The F change is the same, 182. And the DF between is 2, DF within is 47. The significant R squared change is less than 0.001. Most importantly, let's look at the full model. The R squared for full model is 0.888. And it was significant. That is, using full predictors, we significantly predicting SAT score. The R squared change equals to the R squared for the full model minus the R squared for the reduced model. So it is 0.888 minus 0.886, which is 0.002. Here in the model summary, 0.02 tells us the additional R squared explained by the full model, above and beyond the reduced model. So the F-test for R squared change is using this big formula. Okay, so the bottom part is MS residual for the full model. If you look at the ANOVA table, it is 680.403. Then the top part is SS regression for the full model minus SS regression for the reduced model divided by DF regression for the full model minus DF regression for the reduced model. So the top part is 243,689.5 minus 243,069.3 divided by 4 minus 2. F change is 0.456. Then we can look for the to find out the F critical score. The DF between is the DF between for the full model minus DF between for the reduced model. So in our example, it's 4 minus 2, it is 2. DF within is the DF residual for the full model. In our case, it's 45. So we look at the row of 40. The F critical score is positive and negative 3.23. When we compare the F critical score with the F observed score, the F observed score is less than F critical score. Therefore, we fail to reject the null hypothesis. If you look at the model summary, F change is 0.456, DF1 is 2, DF2 is 45, and the significant F change, the p-value is 0.637, it was not significant. Because F critical score is positive and negative 3.23, F's change is less than F critical score, the full model was not significantly better in predicting SAT than the reduced model. delta R squared is 0.002, F parenthesis 2, comma 45 is 0.456. If you understand how to run model comparison between the full model and the reduced model, you can start working on in-class exercise 7.2. Now you can turn in class 7.1 as Lab 7 worksheet. Today we learned multiple linear regression. We reviewed regression coefficients and the significance test, ANOVA table and the F-test, R-square and the significance test for Model 1 and Model 2. Then we explained what is delta R-square, how to conduct the F-test or F-change for delta R-square, how to report the F-test for delta R-square. Next, we explained the multiple correlation coefficient. We then talked about model comparison, such as what are nested models, what is a full model, what is a reduced model. We conducted a model comparison test, such as the F-change score by hand and by SPSS. We learned how to report the results in APA style. Next Tuesday, we will have our second exam. It will be online exam using Lockdown browser. It has 50 multiple choice questions. It is a closed book exam. I have posted the review sheet and the formula sheet onto the Canvas, the folder of file under exam 2. You can also practice, conduct a practice of the locked browser. And when doing the test, you need to keep your camera on, and then you can have your hard copy of the formula sheet and the scratch paper. Good luck, everyone.